Good morning everyone. So welcome to the first session on differential equations, or to be precise on partial differential equations. So before starting with the partial differential equations, we will first see what do you mean by differential equation, and we will classify differential equations. So what do you mean by differential equation? So differential, it's an equation. So it's an equation which involves, or you can say which relates, which involves or which relates a function, and its derivative. So whenever you say an equation which involves a function and its derivatives, then such an equation is called as a differential equation. So that's one thing. So these differential equations are usually categorized as ordinary differential equations and partial differential equations. So what do you mean by an ordinary differential equation? So an equation that involves ordinary derivatives. An equation that involves ordinary derivatives, then such an equation is called as an ordinary differential equation. Means what? That is, one can say this in another way. That means this, if you have only this is important thing. If you have only one independent variable, say x is my independent variable, and suppose your y is what? It's a dependent variable. So what you can do, you can differentiate y with respect to x. This is called as a single derivative. You can take d2y by dx square. You can take third order derivative d cube y upon dx cube, and so on. So these are called as ordinary derivatives. So if you have an equation that involves ordinary derivatives and the independent variable x and the dependent variable y, then combination of this thing, you get an equation, and that equation is called as an ordinary differential equation. So that's what an ordinary differential equation is. Now what do you mean by partial differential equation? So partial differential equation is an equation that involves, these are called as ordinary derivatives. So PDEs are equation which involves partial derivatives. That involves partial derivatives. That means what? You have more than one independent variable. Whenever you have more than one independent variables, if I want to say, suppose your x, y, t, theta, this usually we take as independent variables, and suppose your u is a dependent variable, means your u is what? Your u is depending on x and y. So what I can do is, I can take derivative of u. I can take u with respect to x, I can take u with respect to y, this is one notation, or I can take u with respect to t, because they are independent variables, and my u is what? U is depending on this independent variables. So that's why partial derivative comes into picture. I can take deba square u by deba x square, or deba square u by deba x deba t, and so on. So whenever you have an equation that involves this partial derivatives and this independent variables, then such a differential equation is called as a partial differential equation. So that's how one can see characterization of a differential equation into ODEs and PDEs. So that's one thing. Now let's go to some other characterization of PDEs. So in this playlist, I'm only going to concentrate on partial differential equations. So usually I'm only going to concentrate on PDEs. So usually in my playlist, whenever I say x, y, t, theta, that means I am saying that they are my independent variables. And for dependent variables, I'll be using the variables z and u. Z and u will be my dependent variables. So what is PD? It is nothing but, so you have an equation involving independent variables and the dependent variables. That means if you have a function that involves x, y, t, theta, if you have more than one, if you have some more, and then you have say z, say z with respect to x, z with respect to y, z with respect to xy, and so on. So this is also called as a partial differential equation because it's an equation equal to 0 and it involves a function involving the dependent variable and the partial derivatives. So that's one thing. Okay, so whenever you see a partial differential equation, the basic things that you will come across is the order of a differential equation. Okay, so now let's concentrate on what do you mean by an order of a differential equation. So what is an order? It is nothing but it is the highest derivative that occur in a PDE. Then that is called as the order of a differential equation. Okay, now let's go for the example. So we saw the definition of order. Now let's try to find order of some differential equations. So on the extreme left you will see some 7 examples. All of them are partial differential equations. So let's first of all let's find the order of these differential equations. So if you see the first one, which is uxx plus uyy plus u2t equal to 0. So uxx means what? What do you mean by uxx? It is nothing but del bar square u by del bar x square. And uyy means del bar square u by del bar yy and so on. Okay, so what is the order? So as you can see, this is the second order, this is second order, and as well as this is the second order. So therefore what is the highest order occurring? The highest order occurring is 2. Therefore 2 is the order of this differential equation. Let's go for the second one. So if you can see, the first one is nothing but uxxx means what? This means this is nothing but del bar cube u upon del bar x cube. That means I'm differentiating u with respect to x thrice, plus x square uyy plus u square xy ut is equal to 0. So as we can see, this is third order, this is second order, and this is first order. So what is the highest order occurring? Highest order is nothing but 3. So therefore this is the third order differential equation. For the third example, again if we see the first, this is order 3, this is the first order, this is third order. So highest order is nothing but 3. So this is again a third order partial differential equation. Okay, fourth example, here order is first order partial derivative, this is second order partial derivative. So what is the highest? Highest is nothing but second. So therefore this is also second order. And if you keep on doing this, so this will be second order, this will be second order, and this will be second order. Convince yourself. If you are not convinced, you can ask me in the comment section. So this is what the order of, do you mean by order of a differential equation. Okay, good. Now let's go for the second thing. The second thing is nothing but the cos. When you say a PDE to be a quasi-linear or a quasi-linear PDE, so if the derivatives of the highest order, so you always look at the derivatives of the highest order, and that should be linear, means the degree of that highest order should be 1. So whenever the degree of the highest derivative is 1, then we call such a PDE to be a quasi-linear PDE. So here if you see, the highest order is what? 2, 2, 2. Each of them is having a degree 1. So therefore that means the power is 1. Therefore this is a quasi-linear PDE. If I go for the second one, again this is the highest order. So no need to see, because these are not the highest order, only this is the highest order, so only concentrate here. So what is the degree of uxxx? Again the degree is 1, therefore it is also an example of a quasi-linear. If you go for the third one, which are the highest orders? Here and here, uxxx and uttt, these are the highest order derivatives occurring, and both have the degree 1, so they are also the example of quasi-linear. But if you go for the fourth example, the highest order is 2, and what is the degree of highest order? The degree of highest order is not 1, so therefore this is not a quasi-linear PDE. So, and similarly if you go for the 5th, 6th and 7th, as you can see the highest order is 2 and each of them is having a degree 1, so therefore all of remaining are quasi-linear PDE. So just look at the highest derivative, and if the highest degree is not 1, that means it won't be quasi-linear. Suppose in the first one, if I take uxx square uyy plus utt, so if I make the degree 2, then this is also not a quasi-linear, because all the highest orders should have the degree 1. Even if one of the highest order is not having a degree 1, that means it is not a quasi-linear. Okay, so I hope the meaning of quasi-linear is clear. You simply look at the degree of the highest derivatives. Okay, cool. Let's go for the second categorization, which is nothing but a semi-linear PDE. So what do you mean by a semi-linear partial differential equation? So First of all, it has to be a quasi-linear. First of all, it has to be a quasi-linear, means the degree of highest derivative should be 1. And then you look at the coefficient of the highest derivative. So you look at the highest derivative. The first thing is the degree should be 1. Secondly, you look at the coefficients of those highest derivative. That coefficient should not contain the dependent variable and its derivative. Okay, should not contain the dependent variable and its derivative. Then I will call it as a semi-linear. So first of all, it has to be a quasi-linear. If it is not quasi-linear, it can't be semi-linear. So like for example, this one, this can't be semi-linear. Why? Because first of all, it has to be a quasi-linear. So if it is not quasi-linear, it can't be semi-linear. Okay, good. So now let's play with the remaining 6 examples. So first one, is it semi-linear? Yes. Why so? So you look at the coefficients of the highest derivative. What are the coefficients of the highest derivative? Here it is 1, here it is 1, here it is 1. And that means what? These are 1, 1, 1. The coefficients are 1, 1, 1. That means coefficients do not contain the dependent variable and its derivative. So here you can't see the coefficient as u or u square or something. So therefore this is an example of a semi-linear PDE. Okay, let's go for the second example. Look at the highest order. Okay, it's a quasi-linear and the coefficient of the highest order. So what is the highest order? Only here, u triple x. So no need to see other terms. So the coefficient is what? 1. That means it do not contain u or its derivatives. Therefore this is also an example of a semi-linear. But now let's see the third example. Where are the highest orders? U triple x and u TTT. So these are the two highest order occurring in my differential equation. Now look at the coefficients. Are the coefficients independent of dependent variable and its derivative? Yes, this one it is. But this one, what is the coefficient? U square x. So the coefficient involves u, which is nothing but the dependent variable. So for semi-linear we want it should not contain the dependent variable and its derivative. So therefore for the third example is not a semi-linear because the coefficient of u triple t contains the dependent variable. If you go for the fifth example, is it semi-linear? Again no, because what is the highest order? UTT is the highest order, and if you see the coefficient involves, what is the coefficient? Coefficient is u, so it involves dependent variable. Therefore this is also not a semi-linear PDE. 6th and 7th, yes they are, because what is the highest order? U double x. What is the coefficient? A square. A square is constant, where a is some constant. So therefore 6th and 7th both are semi-linear PDEs. Okay, good. Let's go for the next one. What is the next one? It's when you call something to be a linear PDE. So I call something to be a linear PDE if it has to be a semi-linear, means it has to be quasi-linear, and the coefficients of the highest derivative should not contain dependent variable and its derivative, and moreover you look at all the dependent variables and its derivatives, they should be linear. So in the equations wherever you see dependent variable and its derivative, all should have the degree 1. In that case means everything is very nice. In that case we say it's a linear PDE. So first of all it has to be a semi-linear. So if it is not semi-linear, it can't be linear. So therefore since it's not semi-linear, it can't be linear as well, it can't be linear as well, it can't be linear as well. Okay, good. So now let's go for the first one. It's semi-linear, yes. Plus what, one more thing we want? We want that it is linear in the dependent variable and its derivatives. So we are having the derivatives over here and all of them have degree 1. It has to be linear. That means degree 1. So all of them have degree 1. So therefore this is an example of a linear PDE. Okay, if you go for the second one, dependent variable has to be semi-linear. So yes, it is semi-linear, plus dependent variable and its derivative should have degree 1. Okay, derivative has degree 1. No dependent, it's an independent variable. Degree is 1. Oh, but u is my dependent variable and its degree is not 1. Therefore, it's not a linear PDE. Okay, let's go for 6th and 7th. Okay, dependent variable is not present anywhere, but its derivatives are there. And what is the degree of the derivatives? Degree of the derivatives are 1. So both of them are the linear PDE. So many times linears are always good to play with. If not linear, at least we expect to be semi-linear. And yeah, the last one is the non-linear. So when you call something to be non-linear, if it is not quasi-linear. Okay, if it is not linear, we won't say it's non-linear. Okay, so that's one thing one has to take care of. So when you call something to be non-linear, if it is not quasi-linear, means it should not be quasi-linear, and hence it won't be semi-linear, and hence it won't be linear. So if it doesn't fall into this three category, in short, if it is not quasi-linear, then it can't be, then we say it's a non-linear. So this example is not quasi-linear, that because the degree of the highest derivative is not 1. So since the degree of the highest derivative is not 1, it's not quasi-linear, and hence it is a non-linear differential equation, non-linear partial differential equation, and rest all are quasi-linear, so therefore they do not fall in this category. So when you call something non-linear, if it is not a quasi-linear PDE. So only fourth one is not a quasi-linear, and hence it's a non-linear. So I hope this is clear. Okay, one last thing is about the H and NH, that I have written homogeneous and non-homogeneous. It might not be clear, but yeah, H/NH. NH means non-homogeneous. So when you call something to be a non-homogeneous partial differential equation, okay, so if all the terms in a partial differential equation contains the dependent variable or is partial derivative. So you look at all the terms. If all the terms contains dependent variable or its derivative, then we call it as a homogeneous. And if it do not even if you find even a single term which do not contain the dependent variable or its derivatives, then we call it as a non-homogeneous. Okay, so let's go for the example again. Let's fill up the last column. Look at all the terms. There are 3 terms and all the terms contains the partial derivatives. Therefore, it's an example of a homogeneous PDE. Okay, come for the second example. There are again 3 terms. All the terms contains one of the thing, either u or its partial derivatives. So yes, they contain partial derivatives and they contains u. One of the things should be there. So it's also homogeneous. If you see the third one, these 3 terms, okay, dependent variable ka derivative, dependent variable derivative, dependent variable, so and the derivative. So, but here if you see, this term neither contains the dependent variable nor its derivative. So because of the last term over there, the example number 3rd is an example of a NH, non-homogeneous partial differential equation. Then again, if you go over here, there are 2 terms and both the term contains the partial derivatives, therefore it's a homogeneous. If you go for the 5th one, okay, so these 2 terms contains the dependent variable and the derivatives, but if you see here, my x and t are what? Independent variable. That means this is the term which do not contain the dependent variable u, neither its a derivative. So we are having that one term. Therefore 5th one is also an example of a non-homogeneous PDE. 6th and 7th, both the term contains partial derivatives. Therefore 6th and 7th both are also the examples of homogeneous PDE. So whenever you come across a PDE, make sure you know the order of that PDE. You know whether it is quasi-linear, semi-linear, linear or non-linear, and at the end you should know homogeneous or not. So these are the things. So whenever you see a differential equation, make sure you know this characterization, and then only you proceed further. So that's all about order, linearity, non-linearity and homogeneity of a partial differential equation. Okay, one last thing I want to talk is about the second order linear PDE, because in the coming sessions I am going to discuss about heat and wave equations, and therefore I am only going to give introduction about the second order linear PDE. So what do you mean by a second order linear partial differential equation? So suppose my x and y are independent variables, and suppose u is my dependent variable. Some author use z, some author uses u, but since I am going to discuss about heat and wave equation which will involve u, that's why instead of taking z, I am taking u as my dependent variable. So when I will call something to be a second order linear differential equation, if it is of the following form. Which form? It is of the form a of xy into uxx plus b of xy, second order. That means it will involve second order derivatives uyy plus the lower orders, means plus d of xy into ux plus e of xy into uy plus f of xy into u is equal to g of xy. So if you have such an equation, so you can see it's a second order. Why? Because the highest order occurring is second order derivative, therefore it's a second order. Why it's linear? Because it is quasi-linear. Why it is quasi-linear? Because the degree of the highest order is 1. It's a semi-linear because it's a quasi-linear, plus if you see the coefficient, when you say something to be semi-linear, the coefficient of the highest derivative should not contain the dependent variable or its derivative. So here my dependent variable is u. So if you look at the coefficients of the highest order, they are functions of x and y. A of xy means it's a function of x and y. So the coefficients of the highest order do not contain the dependent variable or its derivative. Therefore it's a semi-linear. And why it's a linear? Because it's a semi-linear, plus none of the terms which contains the dependent variable or its derivative have degree bigger than 1. So here is only the derivative of dependent variable, degree is 1, degree is 1, degree is 1, degree 1, degree 1, degree is 1. And here there is no u or this partial derivatives because they are functions of x and y. So therefore it's a linear partial differential equation. And what is your right hand side? Is some function of x and y. So if that g is 0, we call it to be a, so if my g becomes 0, then I will call it as a second order linear homogeneous partial differential equation. So SOLH means second order linear homogeneous partial differential equation. And if my g is non-zero, then I will call second order linear non-homogeneous partial differential equation. So that's one thing. So, and actually there's one more way of writing it. Usually, I mean, if you see the further classification of second order, I won't be going into that detail, but usually that ABC, these coefficients tell us something more about the second order, because D, E, F, they are the coefficients of the lower orders. And since I'm interested in second order, so if my ABC, so if you consider this coefficient, if you consider this thing, if you consider b square minus 4ac, this is called as a discriminant. This is called as discriminant of 1. What is my 1? Let me call this equation as 1. So you consider b square minus 4ac. So here, if you're this discriminant, so you take a point in a space. So suppose x naught comma y naught comma, yeah, so you take x naught comma y naught. So you take a point in your domain, x naught comma y naught in your domain, in the space, or you take in your domain, and you put that value of x naught y naught in b square minus 4ac. If your b square minus 4ac, if your b square minus 4ac at that point is greater than 0, then we will call that second order PDE to be a hyperbolic PDE. Hyperbolic. Then I will call that my PDE is a hyperbolic partial differential equation. If my discriminant at that point is equal to 0, then I will call my PDE to be a parabolic PDE. And if it is less than 0, then I will call it as an elliptic partial differential equation. So this is further classification. There is, you can do some change of variables, and then you can convert a second order into some standard form, and then you can see whether it is hyperbolic, parabolic and elliptic. But anyways, right now I'm not going to go into that detail. So these are the things that I'll be needing in my coming lectures. So I hope these basics are clear. If you have any concerns, you can ask me in the comment section. Thank you.